Proxima Centauri, the closest star we will never reach. There is a star that sits closer to our sun than any other star in the sky. It has been there for billions of years. It will remain there for trillions more. And despite being our nearest neighbor in a galaxy of hundreds of billions of stars, we cannot reach it. Not with anything we have built, not with anything we know how to build. The distance is simply too great. The star is called Proxima Centauri. The name comes from Latin. Proxima means nearest or next to. Centauri refers to the constellation where it appears in the sky, Centaurus, the centaur. So the name essentially means the nearest star in Centaurus. It was discovered in 1915 by a Scottish astronomer named Robert Innes, who was working at an observatory in South Africa. He noticed a faint point of light moving across the sky in the same direction as a brighter pair of stars known as Alpha Centauri. Further measurements confirmed that this dim object was actually closer to us than those brighter stars, and so it became Proxima. The distance to Proxima Centauri is about 4.24 light-years. That number sounds manageable when you say it quickly, 4.25, a little more than 4, but the light-year is not a small unit. It is not like a mile or a kilometer. A light-year is the distance that light travels in 1 year, moving at its constant speed of about 300,000 kilometers per second. That works out to roughly 9.46 trillion kilometers in a single year. Trillion with a T, so when we say Proxima Centauri is 4.24 light-years away, we are saying it sits at a distance of approximately 40 trillion kilometers from Earth. 40 trillion. That is a 4 followed by 13 zeros. To put this another way, the Sun is about 150 million kilometers from Earth. That distance is called an astronomical unit, and it serves as a useful measuring stick for things inside our solar system. Proxima Centauri is roughly 268,000 astronomical units away, meaning it is 268,000 times farther from us than the Sun is. If you shrank the Earth-Sun distance down to 1 inch, Proxima Centauri would sit about 4.5 miles away on that same scale. The solar system, including the distant orbits of Neptune and Pluto and the scattered objects beyond, would fit within a few dozen inches. The nearest star would still be miles off. This is the fundamental problem. Space is not empty in the sense that it contains nothing interesting. Space is empty in the sense that the interesting things are separated by incomprehensible distances. Even our closest neighbor is functionally unreachable with current technology. And Proxima Centauri is the closest star. Everything else is farther. Proxima Centauri is a type of star called a red dwarf. Red dwarfs are the most common kind of star in our galaxy. Estimates suggest they make up about 3/4 of all the stars in the Milky Way. And yet, despite their abundance, you cannot see a single red dwarf with your naked eye. Not one. They are too dim. Proxima Centauri, even though it is the nearest star to us besides the Sun, has an apparent brightness of about magnitude 11. For reference, the faintest stars you can see on a clear dark night are around magnitude 6. Magnitude 11 is roughly 100 times fainter than that. You need a decent telescope to spot Proxima at all. The reason red dwarfs are so dim is that they are small and cool. Proxima Centauri has a diameter of about 200,000 kilometers. That sounds large until you compare it to the Sun, which is roughly 1.4 million kilometers across. Proxima is only about 1/7 the size of the Sun. In fact, it is only about 1.5 times wider than Jupiter, the largest planet in our solar system. Jupiter is not a star because it lacks the mass to sustain nuclear fusion in its core. Proxima barely crosses that threshold. It contains about 12% of the Sun's mass, which is enough to compress its core to the temperatures and pressures needed for fusion, but not by much. It is a star, but just barely. The surface temperature of Proxima Centauri is around 3,000 Kelvin. The Sun's surface is about 5,800 Kelvin. That difference matters because a star's temperature determines its color. Hotter stars appear bluish-white. Cooler stars appear orange or red. Proxima, with its relatively low temperature, glows with a dim reddish hue. Most of its energy output is in infrared wavelengths rather than visible light. If you were somehow standing on a planet near Proxima, the star would appear much larger than our Sun appears from Earth, because you would need to be very close to receive enough warmth. But it would not be as blindingly bright. The light would be different, redder, softer in some ways, though not necessarily gentler. Red dwarfs have one remarkable quality that sets them apart from larger stars like our Sun. They live for an extraordinarily long time. The Sun is expected to remain stable and burn hydrogen in its core for about 10 billion years total. It is currently around 4.6 billion years into that process, so it has roughly 5 billion years left before it begins to change and eventually swell into a red giant. Proxima Centauri, by contrast, will continue burning hydrogen for something like 4 trillion years. Not billion, trillion. That is 400 times longer than the Sun's entire lifespan. The reason for this extreme longevity has to do with how red dwarfs process their fuel. In a star like the Sun, only the hydrogen in the core gets hot enough to fuse into helium. The outer layers of the star do not participate in fusion. They just sit there, surrounding the core, while the core slowly converts its hydrogen supply into helium ash. When the core runs out of hydrogen, the star has to adjust. It begins burning hydrogen in a shell around the helium core, and this causes the star to expand dramatically. That is the red giant phase. Red dwarfs work differently. Because they are smaller, their interiors are fully convective. Convection is the process where hot material rises, cools, and then sinks back down. In a pot of boiling water, you can see convection happening. The water circulates. In a red dwarf, the entire star circulates in this way. Hot plasma from the core rises to the surface, radiates its heat into space, cools, and sinks back down toward the core. This constant mixing means that fresh hydrogen is continuously being brought into the core from the outer layers. The star does not develop a separate helium core the way the Sun will. Instead, it gradually converts all of its hydrogen throughout its entire volume into helium over an immense span of time. Because of this efficiency, red dwarfs use their fuel very slowly. And because they are constantly mixing new hydrogen into the fusion zone, they have access to nearly all of their hydrogen supply rather than just the 10% or so that sits in the core of a Sun-like star. The result is a stellar lifespan measured in trillions of years rather than billions. No red dwarf anywhere in the universe has yet reached the end of its life. The universe itself is only about 13.8 billion years old. That is far too short a time for even the oldest red dwarfs to have exhausted their fuel. Every red dwarf that has ever formed is still burning. They are all still young, cosmically speaking. Proxima Centauri, despite being older than the Sun, has trillions of years of life ahead of it. It will still be shining long after the Sun has burned out, swelled, shed its outer layers, and collapsed into a white dwarf. Long after the Earth has been consumed or ejected. Long after most of the stars we can currently see have gone dark. Proxima Centauri is part of a larger system. It does not drift through space alone. About 0.2 light-years away from Proxima, there is a pair of much brighter stars called Alpha Centauri A and Alpha Centauri B. These two stars orbit each other with a period of about 80 years. Alpha Centauri A is very similar to the Sun. It is a yellow star, slightly larger and brighter than our own. Alpha Centauri B is a bit smaller and cooler, an orange star, but still reasonably Sun-like. Together, they form a binary system, locked in a gravitational dance that has been going on for billions of years. Proxima Centauri orbits this pair at an enormous distance. Its orbital period around Alpha Centauri A and B is estimated to be about 550,000 years. At its current position, Proxima is roughly 13,000 astronomical units away from the AB pair. That is about 430 times farther from them than Neptune is from the Sun. The orbit is so wide and slow that for a long time, astronomers were not certain whether Proxima was truly bound to the Alpha Centauri system or merely passing through the same region of space by coincidence. Detailed measurements of its motion eventually confirmed that it is gravitationally bound. It is a true member of the system. Alpha Centauri is a triple star system. And Proxima is its smallest, dimmest, and most distant component. From Earth, you cannot see Proxima without a telescope, but Alpha Centauri A and B, seen together as a single point of light, form the third brightest star in the night sky. Only Sirius and Canopus appear brighter. However, Alpha Centauri is only visible from the southern hemisphere and the southernmost parts of the northern hemisphere. If you live in most of Europe, most of North America, or most of Asia, you have never seen Alpha Centauri. It never rises above your horizon. It is a southern star, part of the southern constellation Centaurus, which depicts the mythological creature that was half human and half horse. For those who can see it, Alpha Centauri is a prominent and beautiful object. It has been known since ancient times, but its status as the closest star system to the Sun was not established until the 19th century, when astronomers developed techniques precise enough to measure stellar distances. The method they used is called parallax. Parallax is based on a simple geometric principle that you can demonstrate with your own hand. Hold your thumb out at arm's length and look at it with one eye closed. Then switch eyes. Your thumb will appear to shift against the background. This happens because your two eyes are in slightly different positions, so they see your thumb from slightly different angles. The closer your thumb is to your face, the more it appears to shift. The farther away it is, the less it shifts. Astronomers use the same principle to measure the distances to stars. Instead of using two eyes, they use two positions of Earth in its orbit around the Sun. In January, Earth is on one side of the Sun. In July, it is on the opposite side, about 300 million kilometers away from where it was 6 months earlier. If you observe a nearby star from these two positions, the star will appear to shift slightly against the more distant background stars. The amount of shift is called the parallax angle. For Proxima Centauri, the parallax angle is about 0.77 arcseconds. An arcsecond is a very small unit of angular measurement. There are 3,600 arcseconds in a single degree, and a degree is about twice the width of the full moon as seen from Earth. So 0.77 arcseconds is an extremely tiny shift, but it is measurable. And from that measurement, combined with the known size of Earth's orbit, astronomers can calculate the distance to the star using basic trigonometry. The first successful parallax measurements were made in the 1830s. Thomas Henderson, working in South Africa, measured the parallax of Alpha Centauri. Friedrich Bessel in Germany measured the parallax of a star called 61 Cygni. Friedrich Struve in Russia measured the parallax of Vega. These measurements confirmed what many had suspected. The stars were unimaginably far away. They also established the light year as a useful unit of distance. Bessel noted that light would take about 10 years to travel to 61 Cygni. This was a way of making the distance comprehensible. It was not just a number, it was a duration that people could understand. Light, the fastest thing there is, would need a decade to make the trip. Since then, parallax measurements have become vastly more precise. Ground-based telescopes can measure parallax angles down to about 0.01 arcseconds, allowing distances to be determined for stars within a few hundred light years. The European Space Agency's Hipparcos satellite, which operated from 1989 to 1993, measured parallaxes for over 100,000 stars with unprecedented accuracy. And more recently, the Gaia satellite, launched in 2013, has been measuring the positions and parallaxes of over 1 billion stars. Gaia can detect parallax shifts as small as 10 microarcseconds, which is 10 millionths of an arcsecond. This allows it to map stars across much of the galaxy. Proxima Centauri's distance is now known with extreme precision. The current best value is 4.2465 light-years, with an uncertainty of just a few hundredths of a percent. We know exactly how far away it is. The challenge is not knowing the distance. The challenge is crossing it. Consider the Voyager 1 spacecraft. Launched in 1977, Voyager 1 is currently the farthest human-made object from Earth. It has been traveling through space for over 46 years. It passed through the outer boundary of the solar wind and entered interstellar space in 2012. As of now, it is more than 24 billion kilometers from Earth and still moving outward at about 17 kilometers per second, or roughly 61,000 kilometers per hour. That is fast by human standards. A commercial airplane travels at about 900 kilometers per hour. Voyager is moving nearly 70 times faster than that, and yet, at its current speed, Voyager 1 would take approximately 73,000 years to travel the distance to Proxima Centauri. It is not actually headed in that direction, but if it were, that is how long the journey would take, 73,000 years. To put that in perspective, 73,000 years ago, modern humans had not yet left Africa in large numbers. The last ice age had not yet reached its peak. Writing would not be invented for another 68,000 years. Agriculture would not appear for another 63,000 years. The pyramids of Giza, one of the oldest structures still standing, were built about 4,500 years ago. If you sent a spacecraft to Proxima Centauri at Voyager's speed 4,500 years ago, it would still have more than 68,000 years left to go. The journey is almost incomprehensibly long. The New Horizons spacecraft, which flew past Pluto in 2015, is traveling a bit faster than Voyager 1. It would still take about 54,000 to 80,000 years to reach Proxima, depending on how you calculate its speed. The Parker Solar Probe, which holds the record for the fastest human-made object, reaches speeds of over 700,000 kilometers per hour during its closest approaches to the Sun. At that speed, a trip to Proxima Centauri would take about 6,300 years. That is better than 73,000 years, but still vastly longer than any human institution has ever lasted. The oldest continuously operating organizations on Earth are a few thousand years old at most. We have no idea how to build something that would function reliably for 6,000 years in the hostile environment of interstellar space. The fundamental problem is energy. To travel faster, you need more energy. The relationship is not linear. As you approach high speeds, the energy required to accelerate further increases dramatically. To get a spacecraft up to even 10% of the speed of light would require an amount of energy far beyond anything we can currently produce. And 10% of light speed would still mean a journey of over 40 years to Proxima Centauri. Then there is the problem of slowing down. If you want to do anything other than flash past the star at high speed, you need to decelerate, which requires just as much energy as accelerating did. So you essentially need to carry twice the fuel or find some other way to brake. Various theoretical propulsion systems have been proposed over the years. Nuclear pulse propulsion, where a spacecraft would be pushed forward by a series of nuclear explosions detonating behind it, was studied seriously in the 1950s and 1960s under the name Project Orion. Later concepts like Project Daedalus and Project Icarus explored using fusion reactions to achieve higher speeds. Ion drives, which are currently used on some spacecraft, are very efficient but produce very little thrust, so they would take far too long to build up to interstellar speeds. Solar sails, which use the pressure of sunlight to gradually accelerate, are promising for travel within the solar system, but face challenges at interstellar distances where sunlight grows weak. One proposal that has received attention in recent years is called Breakthrough Starshot. Announced in 2016, this project envisions sending thousands of tiny spacecraft, each weighing just a few grams, to the Alpha Centauri system. These spacecraft would be equipped with miniature cameras and communication equipment. They would be attached to large, thin sails made of reflective material, and they would be accelerated not by sunlight, but by a powerful laser array based on Earth or in orbit. The laser would push the sail, gradually accelerating the tiny spacecraft to perhaps 15 or 20% of the speed of light. At that speed, the journey to Proxima Centauri would take only 20 to 30 years. The concept is elegant in some ways. By making the spacecraft incredibly small and light, you reduce the amount of energy needed to accelerate them. By using a ground-based laser rather than onboard fuel, you avoid the problem of carrying propellant. By sending thousands of spacecraft, you accept that many will be lost to collisions with dust particles or equipment failures, but hopefully some will survive to transmit data back to Earth. However, the engineering challenges are formidable. The laser array would need to be enormous and incredibly powerful, far beyond anything that currently exists. The sails would need to be made of materials that do not exist yet, capable of withstanding intense laser bombardment without melting or tearing. The tiny spacecraft would need to carry functional cameras, computers, and communication systems in a package weighing less than a gram. They would need to survive decades of travel through interstellar space, bombarded by cosmic rays and occasional dust impacts. And they would need to transmit data back to Earth across a distance of 4.24 light-years using a transmitter that weighs almost nothing. The signal would take over 4 years to arrive, and it would be incredibly faint. As of now, Breakthrough Starshot remains in the research phase. No launch date has been announced. The technical problems are being studied, but solutions are not yet in hand. It represents a possible path forward, but not a guaranteed one. It may be that interstellar travel is simply beyond our reach, at least for the foreseeable future. The distances are too vast. The energy requirements are too extreme. The timescales are too long. And yet we can still learn a great deal about Proxima Centauri without traveling there. We can study the light it emits. We can measure how it moves through space. We can detect the gravitational tug of any planets orbiting it. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. It was named Proxima Centauri b. Proxima Centauri b is roughly Earth-sized. Its minimum mass is about 1.07 times the mass of Earth. It was detected using the radial velocity method, which involves watching for tiny wobbles in the star's motion caused by the gravitational pull of an orbiting planet. When a planet orbits a star, the star does not remain perfectly still. It moves in a small circle or ellipse in response to the planet's gravity. This motion causes a slight Doppler shift in the star's light. When the star moves toward Earth, its light is shifted slightly toward the blue end of the spectrum. When it moves away, the light shifts toward the red. By measuring these shifts very precisely, astronomers can infer the presence of a planet and estimate its mass. Proxima Centauri b orbits very close to its star. Its orbital period is only 11.2 Earth days. That means a year on Proxima b lasts less than 2 Earth weeks. The planet sits about 7.5 million kilometers from Proxima Centauri. For comparison, Mercury, the innermost planet in our solar system, orbits about 58 million kilometers from the Sun. Proxima b is nearly 8 times closer to its star than Mercury is to ours. Despite this extreme proximity, Proxima b receives roughly the same amount of energy from its star that Earth receives from the Sun. This is because Proxima Centauri is so much dimmer than the Sun. The habitable zone around a red dwarf, the region where liquid water could potentially exist on a planet's surface, lies much closer to the star than it would around a brighter star. Proxima b sits within this habitable zone. This fact generated considerable excitement when the discovery was announced. The closest exoplanet to Earth, orbiting the closest star to the Sun, is potentially habitable. But potential habitability is not the same as actual habitability. Many factors determine whether a planet can support life or even just support liquid water on its surface. The mere fact that a planet is in the habitable zone does not guarantee anything. Venus is sometimes considered to be within the Sun's habitable zone, or at least near its inner edge. Mars is within the outer edge. Neither planet has liquid water on its surface today. Venus is far too hot, with a runaway greenhouse effect and a crushing atmosphere. Mars is too cold and has lost most of its atmosphere to space. Being in the habitable zone is a necessary but not sufficient condition for habitability. Proxima b faces several challenges that Earth does not. First, it is almost certainly tidally locked to its star. Tidal locking is a phenomenon where a body's rotational period matches its orbital period, so the same face always points toward the object it is orbiting. The Moon is tidally locked to Earth. You always see the same side of the Moon. Proxima b is likely tidally locked to Proxima Centauri. This means one hemisphere of the planet would experience permanent daylight, always facing the star, while the other hemisphere would be in permanent darkness, always facing away. This creates extreme temperature differences. The day side could be very hot. The night side could be extremely cold, possibly cold enough to freeze any atmosphere that accumulated there. Whether a tidally locked planet can maintain habitable conditions depends on many factors, including whether it has an atmosphere thick enough to transport heat from the day side to the night side, and whether that atmosphere is stable over long periods of time. Second, Proxima Centauri is a flare star. Red dwarfs in general, and Proxima in particular, are prone to sudden, violent outbursts called stellar flares. During a flare, the star's brightness can increase dramatically, and it emits intense bursts of ultraviolet radiation and X-rays. Proxima produces flares roughly 5 times per year on average, some of them quite powerful. In 2019, astronomers observed the largest stellar flare ever recorded from Proxima, one that made the star temporarily 14,000 times brighter in ultraviolet wavelengths than normal. This radiation would batter any planet orbiting close to Proxima. On Earth, our magnetic field and thick atmosphere protect us from most of the sun's harmful radiation. But Proxima b, orbiting so close to an active flare star, would receive far more radiation than Earth does. Some models suggest that this radiation could strip away a planet's atmosphere over millions of years, leaving it bare and lifeless like the Moon or Mercury. Other models suggest that under the right circumstances, an atmosphere might survive, especially if the planet has a strong magnetic field or started with a very thick atmosphere that could afford to lose some material over time. We do not know which scenario applies to Proxima. We do not even know for certain whether it has an atmosphere at all. The discovery of Proxima b was confirmed using careful analysis of radial velocity data collected over many years. Since then, additional planets have been identified in the system. In 2022, astronomers confirmed the existence of Proxima Centauri d, a planet even smaller than Earth, with a mass of about 1/4 of Earth's mass. It orbits much closer to the star than Proxima b, with an orbital period of just 5.1 days. At that distance, it would be far too hot to be habitable. There is also a candidate planet called Proxima Centauri c, which would be a much larger world, perhaps 7 times the mass of Earth, orbiting much farther out with a period of about 5 years. However, the evidence for Proxima c is disputed. Some astronomers believe the signal that was interpreted as a planet might actually be caused by stellar activity or other systematic effects in the data. Its existence remains uncertain. So our nearest stellar neighbor has at least 2 confirmed planets and possibly a third. One of them, Proxima b, sits in the habitable zone and is roughly Earth-sized. It is the closest exoplanet to Earth, and yet we know very little about it beyond its mass and orbit. We do not know if it has an atmosphere. We do not know if it has water. We do not know if it has a magnetic field. We do not know what its surface is like. All of these things would require either much more powerful telescopes than currently exist, or ideally, a spacecraft that could visit the system and send back data. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built. It observes primarily in infrared wavelengths and can detect faint, distant objects that previous telescopes could not see. However, even Webb is not powerful enough to image Proxima b directly or analyze its atmosphere in detail. The planet is too close to its star and too faint. Future telescopes, currently being designed and proposed, may eventually have the capability to study Proxima b's atmosphere by analyzing how starlight passes through it during a transit. But Proxima b may not transit its star from our line of sight, in which case this technique would not work. The geometry has to be just right. Ground-based telescopes are also improving. New extremely large telescopes with mirrors 30 or 40 meters across are under construction and expected to begin operations in the coming years. These may be able to directly image exoplanets that are currently beyond reach, but the challenges are significant. Proxima b, orbiting so close to its star, would appear very close to the star in any image, and separating the faint light of the planet from the bright glare of the star is extraordinarily difficult. We are at an interesting moment in the history of astronomy. We know that planets exist around nearly every star. We know that some of those planets orbit in the habitable zones of their stars. We know that one such planet orbits the closest star to the Sun. But we cannot yet determine whether any of these planets are actually inhabited or even whether they have the basic conditions that might allow life to exist. The knowledge and the limitations sit side by side. Light from Proxima Centauri takes about 4.24 years to reach Earth. When you look at Proxima through a telescope, you see it as it was 4.25 years ago. This is true for all astronomical observations. The farther away an object is, the older the light you are seeing. The Sun's light takes about 8 minutes to reach Earth, so you see the Sun as it was 8 minutes ago. The light from the Andromeda galaxy takes 2.5 million years to reach us, so we see Andromeda as it was 2.5 million years ago. In a sense, looking at the night sky is looking into the past. For Proxima Centauri, the delay is modest. 4 years is not long. If something dramatic happened at Proxima, if the star suddenly brightened or one of its planets changed in some detectable way, we would know about it within a few years. But 4 years is still a significant communication lag if you were trying to operate a spacecraft there. Any signal sent from Earth would take 4.24 years to arrive. Any response would take another 4.24 years to come back. A simple exchange of messages would require nearly 9 years. This is one of the many reasons why interstellar spacecraft, if they are ever built, would need to be highly autonomous. You could not control them in real time the way mission controllers guide rovers on Mars, where the signal delay is only about 20 minutes at most. A spacecraft at Proxima would be on its own. It would need to make decisions, navigate hazards, point its cameras and instruments, and compress and transmit data, all without waiting for instructions from Earth. The artificial intelligence and reliability requirements are beyond anything we have achieved so far. But these are problems for future generations to solve, if indeed they are solvable at all. For now, Proxima Centauri remains what it has always been, a faint red point of light in the southern sky, visible only through telescopes, circling the brighter pair of Alpha Centauri stars in an orbit that takes hundreds of thousands of years to complete. It is our nearest stellar neighbor. It will remain so for another 25,000 years or so, until the slow motion of stars through the galaxy brings other suns closer. Eventually, Proxima will drift farther away, and other stars will take its place as the nearest neighbor. But for the foreseeable future, as measured in human lifetimes, it is and will remain the closest star beyond the Sun. The fact that we cannot reach it does not diminish its significance. If anything, it highlights something important about our place in the universe. We live on a small planet orbiting an ordinary star in the outer regions of an ordinary galaxy. The nearest other star is so far away that crossing the distance would take tens of thousands of years with our best current technology, or perhaps a few decades with technology that does not yet exist and may never exist. The universe is vast, almost beyond comprehension, and we occupy only a tiny corner of it. This is not a reason for despair. It is simply a description of reality. We can still study the universe. We can still learn about distant stars and planets and galaxies. We can still ask questions about how the cosmos formed and how it will evolve and whether life exists elsewhere. The answers may take centuries or millennia to find, if they can be found at all. But the search itself has value. Understanding where we are and what surrounds us is part of what makes us human. Proxima Centauri is a red dwarf. It is small and cool and dim. It is the most common type of star in the galaxy, and yet until 1915, no one knew it existed. It has at least 2 planets, possibly 3. One of those planets is roughly the size of Earth and sits in the habitable zone. We cannot visit it. We cannot even see it clearly, but we know it is there. In about 4 trillion years, long after the Sun has exhausted its fuel and Earth has been destroyed or ejected, Proxima Centauri will still be burning. It will be old by then, older than the current age of the universe by a factor of hundreds, but it will still be a star. Red dwarfs are the last stars to form and the last stars to die. When the universe is many times its current age, when most of the larger stars have gone dark, the red dwarfs will still be glowing. They will be the final embers in a cooling cosmos. Whether anyone will be around to see them is another question. Life as we know it evolved on a planet orbiting a medium-sized yellow star in a universe still relatively young. We have no idea whether life could exist on a planet orbiting a red dwarf, or whether civilizations could arise and persist for the trillions of years that such stars will continue to shine. These are questions without answers, for now. Perhaps someday we will know more. The Alpha Centauri system has 3 stars. Alpha Centauri A is the largest and brightest, a yellow star very similar to the Sun. It is about 10% more massive than the Sun and about 50% more luminous. If you were standing on a hypothetical planet orbiting Alpha Centauri A at the same distance Earth orbits the Sun, the star would look much like our Sun looks from Earth. Slightly brighter, perhaps, but recognizably similar, a yellow star in a blue sky. Alpha Centauri B is smaller and cooler, an orange star with about 90% of the Sun's mass and less than half its luminosity. From a planet at the right distance, it would appear larger in the sky than the Sun does from Earth, because you would need to be closer to receive the same amount of warmth. Orange stars are not as hot as yellow stars, so their habitable zones are closer in. But they are also less prone to flares than red dwarfs, which might make them more hospitable to life. Alpha Centauri A and B orbit each other with a period of about 80 years. Their separation varies over the course of that orbit. At their closest, they are about 11 astronomical units apart, roughly the distance from the Sun to Saturn. At their farthest, they are about 36 astronomical units apart, roughly the distance from the Sun to Pluto. This variation means that any planets in the system would experience changing conditions over time as the two stars moved closer together and then farther apart. The gravitational influence of the second star could also destabilize planetary orbits, making it difficult for planets to form or persist in certain regions. No planets have been confirmed around Alpha Centauri A or B so far. There have been claims and retractions over the years. In 2012, a team announced the detection of a planet around Alpha Centauri B, but subsequent analysis suggested the signal was probably a false positive caused by systematic errors in the data. The search continues. If Earth-sized planets exist in the habitable zones of these sun-like stars, they would be prime targets for study. But detecting such planets is difficult, especially in a binary system where the gravitational dynamics are complex. Proxima Centauri is the third member of this system, but it is so far from the other two stars that it almost feels like a separate system. The distance from Proxima to the AB pair is about 13,000 astronomical units. Light takes about 0.2 years, or about 2.5 months, to travel from the AB pair to Proxima. The gravitational bond between them is weak but real. Proxima is slowly orbiting the other two, taking over 500,000 years to complete each orbit. From Proxima's perspective, Alpha Centauri A and B would appear as two very bright stars in the sky, brighter than any star appears from Earth, but not close enough to provide significant warmth. If intelligent beings existed on a planet around Proxima, they would see the AB pair as a brilliant double star. At times, the two would be close together. At other times, they would appear separated. The changing configuration would be visible over a human lifetime. Over many centuries, the pair would trace out their 80-year orbit, swinging closer together and then farther apart. It would be a striking sight. Two bright suns, thousands of times brighter than any star we see from Earth, dancing in the darkness. But of course, we have no evidence that intelligent beings exist on Proxima B or anywhere else. We have not found any signs of life beyond Earth. The search continues. Radio telescopes scan the sky for artificial signals. Space missions look for biosignatures in the atmospheres of planets in our own solar system. Future telescopes will search for biosignatures in the atmospheres of exoplanets. So far, the search has come up empty. This does not mean life does not exist elsewhere. It may just mean we have not yet developed the tools or looked in the right places, or it may mean we are alone. The data do not yet allow us to distinguish between these possibilities. The question of whether life exists beyond Earth is one of the oldest questions humans have asked. For most of history, it was purely philosophical. We had no way to investigate it scientifically. We did not even know that other stars had planets. The first confirmed exoplanet was not discovered until 1992, and it orbited not a normal star but a pulsar, the spinning remnant of an exploded star. The first exoplanet around a sun-like star was found in 1995. Since then, thousands of exoplanets have been discovered, and statistical analysis suggests that most stars have at least one planet. Planets are common. The question is whether life is common. Proxima B offers a tantalizing but frustrating test case. It is right next door, astronomically speaking. It is in the habitable zone. It is roughly the right size, but we cannot determine whether it has life or even whether it has the conditions that might allow life to exist. The information we need is locked away, 4.24 light-years distant, on a world we cannot yet see clearly and certainly cannot visit. Perhaps future generations will answer these questions. Perhaps they will build telescopes powerful enough to image Proxima b directly and analyze its atmosphere. Perhaps they will build spacecraft capable of reaching the Alpha Centauri system within a human lifetime. Perhaps they will find signs of life, or prove that Proxima b is barren and lifeless. Or perhaps they will find that the challenges are simply too great, that interstellar travel remains forever beyond our reach, and that we must content ourselves with studying our cosmic neighbors from afar. Either way, the effort to understand our place in the universe will continue. That is what humans do. We ask questions, we build tools to help answer them, we push against the limits of what we can know and see and reach. The fact that the universe does not make it easy is not a discouragement. It is simply the nature of the problem. Proxima Centauri has been our nearest stellar neighbor for about 32,000 years. It will remain so for another 25,000 years or so. After that, the continuing motion of the stars through the galaxy will slowly change the neighborhood. Other stars will drift closer. Proxima will drift farther. In about 26,700 years, according to current calculations, the star that will be closest to the Sun will not be Proxima Centauri, but rather Ross 248, a red dwarf currently about 10 light-years away, but approaching us. Eventually, Ross 248 will pass by and recede, and other stars will take its turn as nearest neighbor. This stellar shuffle has been going on for billions of years and will continue for billions more. Stars are not fixed points. They orbit the center of the galaxy, each on its own path. The Sun orbits the galactic center once every 230 million years or so. Other stars have different orbits, faster or slower, inclined at different angles. Over millions of years, these differences cause stars to drift past each other. Close encounters are rare, but not impossible. There have probably been stars that came much closer to the Sun than Proxima currently is, passing through the outer reaches of the solar system and disturbing the orbits of distant comets. There will probably be more such encounters in the future. But for now, in our current era, Proxima Centauri holds the title of closest star. It is a title without practical meaning since we cannot reach it, but it has symbolic meaning. When we look at Proxima, we are looking at the minimum distance that separates us from the rest of the stellar universe. Everything else is farther. If Proxima is out of reach, then so is everything beyond it. Unless, of course, we find a way to reach it. Physics does not forbid interstellar travel. It only makes it very difficult. The speed of light is a hard limit, but even a small fraction of the speed of light would be enough to reach Proxima Centauri within a few decades. The challenges are engineering challenges, not fundamental physical barriers. Energy storage, propulsion efficiency, spacecraft durability, communication over interstellar distances, navigation in the void. These are hard problems, but they are not impossible problems in principle. History has shown that technological progress can solve problems that once seemed insurmountable. 150 years ago, the idea of humans flying through the air seemed fanciful. 100 years ago, the idea of sending objects into space seemed like science fiction. 60 years ago, humans walked on the moon. What will be possible in another 60 years, or 600, or 6,000? No one can say. Predictions about future technology are notoriously unreliable. Some things turn out to be easier than expected, others turn out to be harder. Some technologies plateau, others experience sudden breakthroughs. The future is not predetermined. It depends on choices and discoveries that have not yet been made. What we can say is that Proxima Centauri will still be there whenever we are ready. It is not going anywhere. It will continue to orbit Alpha Centauri A and B. It will continue to spin on its axis. It will continue to shine with the dim red glow of a star that will burn for trillions of years. If we ever develop the ability to send a spacecraft there, Proxima will be waiting. In the meantime, we study it from afar. We measure its light. We track its motion. We search for signs of planets and try to understand their properties. We ask whether conditions there might allow for life. We fit Proxima into our larger understanding of stars and stellar evolution and planetary formation. We use it as a benchmark, a reference point, a reminder of both how far we have come in understanding the universe and how far we still have to go. Red dwarfs were once thought to be unlikely hosts for habitable planets. They were too dim, too prone to flares, too likely to tidally lock their planets. The habitable zones were too close, the radiation environments too harsh. But as our knowledge has grown, the picture has become more complicated. Red dwarfs may indeed be hostile in some ways, but they also have advantages. Their long lifespans provide enormous amounts of time for life to evolve, far more than sun-like stars offer. Their abundance means that if even a small fraction of red dwarf planets are habitable, the total number of habitable worlds in the galaxy could be very large. Proxima Centauri is just one example. There are billions of red dwarfs in the Milky Way. Many, perhaps most, have planets. Some of those planets are in habitable zones. We cannot study all of them in detail, but we can study Proxima because it is close. What we learn from Proxima may apply to countless other systems we will never see. The star itself is unremarkable in many ways. It is not particularly large or small for a red dwarf. It is not particularly young or old. It is not particularly active or quiet. It is just a star, one of hundreds of billions in the galaxy. But it happens to be the closest one to us, and that makes it special in a way that no other star can match. 40 trillion kilometers, that is the distance, a number so large that it loses meaning. You cannot picture 40 trillion kilometers. Your brain is not built to handle quantities of that size. You can understand it abstractly, as a calculation, as a string of digits, but you cannot feel it the way you feel the distance across a room or across a city. It is simply too big. And yet it is also the smallest interstellar distance. Proxima is as close as any star gets. Beyond it, the numbers grow larger. The next nearest star after the Alpha Centauri system is Barnard's star, about 6 light-years away. Then Wolf 359 at about 7.8 light-years. Then Lalande 21185 at about 8.3 light-years. And so on, out into the depths of the galaxy, where the distances are measured in hundreds and thousands and tens of thousands of light-years. The Milky Way is about 100,000 light-years across. Proxima Centauri is at the very closest edge of what lies beyond our solar system. If the galaxy were a large city, Proxima would be the house next door. But even next door is too far to walk when each step covers only a tiny fraction of the distance and your legs can only carry you so fast. We have spoken about Proxima Centauri, about its properties as a star, about its planets, about the challenges of reaching it, about what we might learn if we could. But there is another aspect worth considering, the view from the other side. If you stood on Proxima Centauri b and looked up at the sky, what would you see? Assuming the planet has a thin atmosphere or no atmosphere at all, the sky would appear black and filled with stars, much as it does from the moon. But the stars would be in slightly different positions. The constellations would look subtly different, and one star in particular would stand out. Our sun would appear as a bright star in the sky of Proxima, not the brightest star, but certainly one of the brighter ones. It would appear in the constellation Cassiopeia from that vantage point, somewhat disrupting the familiar W shape that we see from Earth. The sun would have an apparent magnitude of about 0.4, similar to the brightness of Procyon or Achernar as seen from Earth. A noticeable star, but not an overwhelming one. If there were astronomers on Proxima b, and if they had developed the technology to detect planets around other stars, they might have detected Earth. They would have seen a small planet orbiting a yellow star at a distance of about 1 astronomical unit. They would have measured its orbital period at about 365 days. If their instruments were sensitive enough, they might have detected the presence of oxygen and water vapor in Earth's atmosphere, potential signs of a habitable or even inhabited world. But they would face the same challenges we face. They would be unable to visit. They would have to content themselves with studying Earth from afar, just as we study Proxima b from afar. They would know a planet existed, but not what it looked like up close. They would speculate about whether it harbored life without being able to confirm their suspicions. This symmetry is worth noting. The universe does not privilege any particular location. The laws of physics are the same everywhere. The challenges of interstellar travel are the same whether you start from Earth or from Proxima b. If there are beings there, they face the same immense distances, the same energy requirements, the same limitations on communication. They are not coming to visit us any more than we are going to visit them. Unless, of course, something we do not understand is possible. Wormholes, warp drives, other speculative technologies that have been explored in science fiction and occasionally in serious physics papers. These remain firmly in the realm of theory and speculation. No evidence suggests that faster-than-light travel or instantaneous travel across vast distances is achievable. General relativity, our best theory of gravity and the structure of space-time, does not obviously forbid such things, but it also does not obviously allow them. The energy requirements appear to be astronomical, perhaps literally impossible, and no one has demonstrated anything approaching a working prototype. For now, the universe appears to enforce a cosmic speed limit. Light moves at 300,000 kilometers per second. Nothing with mass can travel that fast. Approaching the speed of light requires more and more energy without limit. And even at the speed of light, crossing the galaxy would take 100,000 years. The observable universe would take billions of years to cross. We live in a universe of immense distances and finite speeds. That is simply how things are. It is neither good nor bad. It is not designed to frustrate us or to inspire us. It is just the physical reality within which we exist. Learning to accept that reality while still pushing against its limits where possible is part of the scientific enterprise. Proxima Centauri will be there tomorrow. It will be there next year. It will be there when you are old, and when your grandchildren are old, and when civilizations rise and fall and rise again. It has been there since before the Earth formed and will be there long after the Earth is gone. It is patient in a way that nothing human can be patient because it is not trying to do anything or go anywhere. It is just a star burning quietly in the dark. End of part 1. Part 2. The light that reaches us from Proxima Centauri tonight left the star about 4 years and 3 months ago. That is a common way to think about astronomical distances. The numbers become slightly more graspable when you convert them from spatial units to temporal ones. Instead of asking how many kilometers separate us from Proxima, you ask how long its light has been traveling. At the speed of 300,000 kilometers per second, light covers enormous distances in short amounts of time by human standards. In 1 second, it can travel far enough to go around Earth more than 7 times. In 1 minute, it travels about 18 million kilometers. In 8 minutes and 20 seconds, it crosses the 150 million kilometers from the Sun to Earth. That is why we say the Sun is about 8 light minutes away. If the Sun suddenly went dark, we would not know about it for 8 minutes and 20 seconds. We would still see its light, still feel its warmth for that brief interval, then darkness would arrive. For the Moon, the delay is much shorter. Light takes about 1.3 seconds to travel from the Moon to Earth. That is why when astronauts were on the Moon during the Apollo missions, there was a noticeable but manageable delay in communications. Houston would ask a question. About 1.3 seconds later, the astronauts would hear it. They would respond. About 1.3 seconds later, Houston would hear the response. A total round-trip delay of about 2.6 seconds. Annoying, perhaps, but workable. For Mars, the delay is more significant. At its closest, Mars is about 55 million kilometers from Earth. Light takes about 3 minutes to cross that distance. At its farthest, Mars can be over 400 million kilometers away, making the light travel time about 22 minutes. Operating the rovers that have explored Mars requires patience. You cannot drive them in real time. You send a command, wait for it to arrive, wait for the rover to execute it, wait for the confirmation signal to come back. The round trip can take anywhere from 6 minutes to nearly 45 minutes, depending on where Earth and Mars are in their orbits. Now consider Proxima Centauri. The light travel time is not minutes, it is years. If you sent a radio signal to Proxima at the speed of light, it would arrive in about 4.24 years. If someone or something at Proxima sent a reply immediately, that reply would take another 4.24 years to reach us. The round-trip communication time would be about 8.5 years, nearly a decade, just to exchange a single message. This is why any spacecraft sent to another star would need to be largely autonomous. You could not control it from Earth. The delays would be far too long. The spacecraft would need to carry all its instructions with it, or be capable of making its own decisions based on what it encountered. It would need to navigate, adjust course, respond to unexpected situations, point its instruments, and transmit data, all without waiting for guidance from home. We have some experience building autonomous spacecraft. The Voyager probes, now in interstellar space, operate on pre-programmed instructions with limited ability to respond to new situations. They send data back and receive occasional updates, but they are not truly autonomous in a sophisticated sense. Mars rovers have more autonomy. They can plan short drives on their own, avoiding obvious obstacles, but they still rely heavily on commands from Earth. A truly interstellar probe would need capabilities far beyond what any current spacecraft possesses. Artificial intelligence research has made significant progress in recent decades. Machines can now recognize images, understand speech, play complex games, and generate human-like text. But the kind of AI that would be needed for an interstellar mission is different. It would need to be reliable over decades without human intervention. It would need to operate with limited power and computational resources. It would need to adapt to situations that no one anticipated. And it would need to do all this while traveling through an environment that is poorly understood and potentially hazardous. Interstellar space is not perfectly empty. It contains a thin scattering of atoms and molecules, mostly hydrogen. It contains dust particles, some as small as grains of sand or smaller. It contains cosmic rays, high-energy particles that can damage electronics and biological tissue. At high speeds, even tiny particles become dangerous. A grain of dust that would be harmless if you walked into it becomes a serious threat when you are traveling at thousands or millions of kilometers per hour. The kinetic energy of a collision depends on speed squared, double your speed, and the energy of impact quadruples. At a significant fraction of the speed of light, a grain of dust could punch through a spacecraft's hull like a bullet. This is one of the reasons why some proposals for interstellar travel focus on sending very small spacecraft rather than large ones. A tiny probe might survive a dust impact that would destroy a larger craft, simply because there is less of it to hit. It is also easier to accelerate a tiny probe to high speed, since the energy required scales with mass. A gram-scale spacecraft requires far less energy to accelerate than a ton-scale spacecraft. But tiny spacecraft have their own limitations. They cannot carry much equipment. Their transmitters are limited by power and antenna size. Sending a signal across 4.24 light-years requires a substantial amount of energy, and the signal spreads out over that distance, becoming fainter and harder to detect. A tiny transmitter might produce a signal that is simply too weak to be picked up by any receiver on Earth, no matter how sensitive. One proposed solution is to have many tiny spacecraft travel together and coordinate their transmissions. By timing their signals precisely, they could create an effect similar to a larger antenna, boosting the combined signal strength. This requires sophisticated coordination among the spacecraft, which adds complexity. It also requires that many of the spacecraft survive the journey and arrive at the destination functioning. If the loss rate is high, you need to send thousands of probes to ensure that enough arrive to form a useful swarm. These are the kinds of engineering problems that would need to be solved to send even the simplest probe to another star. They are not impossible problems in principle. Each one has potential solutions, but the solutions themselves create new problems, and the overall challenge is staggering. It is not surprising that no one has attempted an interstellar mission. The technology simply does not exist yet, and it may not exist for a very long time. In the meantime, we continue to learn about Proxima Centauri and its planets using only the light that reaches us. Light carries information. By analyzing how that light varies in intensity, in color, in the timing of its arrival, astronomers can deduce a remarkable amount about distant objects. Spectroscopy is one of the most powerful tools. When light passes through a gas, certain wavelengths are absorbed by atoms in the gas. Each element absorbs a characteristic set of wavelengths, leaving dark lines in the spectrum. By examining these lines, astronomers can determine what elements are present in a star's atmosphere, or in the atmosphere of a planet if it passes in front of its star. This technique has been used to identify hydrogen, helium, sodium, water vapor, methane, and many other substances in the atmospheres of exoplanets. For Proxima Centauri b, spectroscopic analysis is difficult because the planet is so close to its star and the star is so much brighter. The planet's signal is overwhelmed by the star's light. Separating the two requires either blocking the starlight with a special mask called a coronagraph or waiting for a moment when the planet passes directly in front of the star, causing a tiny dip in the star's brightness. This is called a transit. Transits are how many exoplanets have been discovered. When a planet crosses in front of its star as seen from Earth, it blocks a small amount of the star's light. The amount of dimming depends on the size of the planet relative to the star. For an Earth-sized planet around a Sun-like star, the dimming is about 0.01%. This is small but detectable with precise instruments. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets using this transit method. But transits only happen if the planet's orbit is aligned just right. The orbital plane must be oriented so that the planet passes between the star and Earth. For most planets, this does not happen. Their orbits are tilted at angles that cause them to pass above or below the line of sight to the star. Proxima b may or may not transit its star from our perspective. Observations so far have not detected a transit, which could mean either that the planet does not transit or that the transit is too shallow or too brief to have been caught. The uncertainty remains. If Proxima b does transit, future telescopes might be able to detect the tiny amount of starlight that passes through the planet's atmosphere during the transit. This starlight would carry spectral signatures of whatever gases are present. Finding oxygen, water vapor, or methane could suggest a potentially habitable environment. Finding certain combinations of gases that would not persist without being replenished could suggest active chemistry or even biology. This is the dream of astrobiologists, detecting biosignatures in the atmosphere of an exoplanet. But we are not there yet. Current technology cannot perform this measurement for Proxima. The planet is too faint, the star too bright, the transit uncertain. It may be decades before we have the instruments capable of characterizing Proxima b's atmosphere in detail, if such characterization is possible at all. There is also the question of what we would do if we found signs of life. How would we confirm them? How would we rule out non-biological explanations? The history of astrobiology is full of false alarms and ambiguous results. Mars has shown tantalizing hints of possible microbial life over the years, none of which have been confirmed. The Viking landers in the 1970s conducted experiments that some scientists interpreted as positive evidence for life, while others interpreted them as chemical reactions in Martian soil. The debate continues to this day. Finding life, if it exists, will not be easy. Proving that we have found life will be even harder. Extraordinary claims require extraordinary evidence, and a claim that life exists on another planet is about as extraordinary as claims get. The scientific community will demand rigorous proof, multiple independent lines of evidence, consideration of all alternative explanations. It is not enough to see something that looks like a biosignature. You have to rule out every non-biological process that might produce the same result. For Proxima b specifically, the challenges are compounded by the harsh radiation environment. Even if the planet once had life, or currently has life, the intense flares from its star might make surface life impossible. Any life would likely need to shelter underground or underwater, protected from the ultraviolet and X-ray bombardment. Detecting such hidden life from a distance of 4.24 light-years would be extraordinarily difficult. None of this means we should stop looking. The search for life beyond Earth is one of the most profound scientific endeavors humans have ever undertaken. Whether we find life or not, the search itself tells us something about the universe and our place in it. If life is common, that suggests something about the nature of chemistry and the conditions under which complex molecules organize themselves into living systems. If life is rare, that suggests something about how special and precious life on Earth truly is. Either answer is meaningful. Let us return to the star itself. Proxima Centauri is classified as an M-type star, specifically M55. The letter M indicates the coolest category of stars in the standard classification system, which runs from O through B. A, F, G, K, and M. O-type stars are the hottest and most massive, burning with a blue-white light. They are rare and short-lived, exhausting their fuel in just a few million years. M-type stars are the coolest and least massive, burning with a red or orange light. They are the most common stars in the galaxy and the longest-lived. The number after the letter, the 5.5 in M55, indicates where within the M category the star falls. M0 is the hottest M-type star, similar in some ways to cooler K-type stars. M9 is the coolest, right at the boundary with brown dwarfs, which are objects too small to sustain nuclear fusion and thus not true stars. Proxima Centauri, at M55, sits in the middle of the range. It is cooler than most red dwarfs, hotter than the coolest ones. A fairly typical example of its class. Brown dwarfs are sometimes called failed stars. They form the same way stars do, from collapsing clouds of gas and dust. But they do not accumulate enough mass to compress their cores to the temperatures and pressures needed for sustained hydrogen fusion. They may fuse a little bit of deuterium, a heavier form of hydrogen, in their youth, but this quickly runs out. After that, they simply cool and fade over time, glowing dimly in infrared wavelengths, but not producing the sustained energy output of a true star. Proxima Centauri is above this threshold. It has about 12% of the Sun's mass, which is enough to maintain hydrogen fusion in its core, but it is not far above the threshold. Stars smaller than about 5% of the Sun's mass become brown dwarfs rather than true stars. Proxima is less than twice this limit. It is one of the smallest and coolest objects that can still be called a star. Because it is fully convective, mixing material throughout its interior, Proxima will gradually convert all of its hydrogen into helium over its immensely long lifespan. Larger stars like the Sun do not do this. They only burn the hydrogen in their cores, leaving the rest untouched. When the core runs out of hydrogen, they undergo dramatic changes. They swell into red giants. They may shed their outer layers into space, forming beautiful planetary nebulae. Eventually, their cores collapse into white dwarfs, dense remnants about the size of Earth, but with the mass of the Sun. Red dwarfs skip most of this drama. Because they burn their fuel so slowly and completely, they do not go through a red giant phase. Instead, as they exhaust their hydrogen supply over trillions of years, they gradually shrink and heat up, becoming what astronomers call blue dwarfs. A blue dwarf is a theoretical stage in stellar evolution that no star has yet reached, because the universe is not old enough. Eventually, blue dwarfs would cool into white dwarfs, the final stellar remnants. But this process takes so long that it will not happen to any red dwarf for many trillions of years. Proxima Centauri is about 4.85 billion years old, roughly the same age as the Sun. Both stars formed around the same time, in the same general region of the galaxy. They may have formed from the same giant molecular cloud, though they are not close enough to be considered siblings. Over the past nearly 5 billion years, both stars have been quietly burning hydrogen, producing light and heat. Both have had plenty of time for planets to form around them, and potentially for life to arise on those planets. The similarity in age is somewhat coincidental. Stars form continuously throughout the galaxy, and there is no particular reason why the nearest star should be the same age as the Sun. It just happens to be. If you picked a random star in the galaxy, it might be much younger or much older. But the galaxy has been forming stars for about 13 billion years, and most of the stars in the galactic disk are between 1 and 10 billion years old, so ages similar to the Sun's are common. Proxima Centauri has about 4 trillion years of life ahead of it, give or take. This is a difficult number to comprehend. The universe is currently about 13.8 billion years old. Proxima will continue burning for roughly 300 times longer than the current age of the universe. In 4 trillion years, the Milky Way and Andromeda galaxies will have merged. Many of the stars we see today will have died. New stars will have formed and died. The universe will be a very different place, and Proxima Centauri will still be there, glowing faintly in whatever cosmic environment surrounds it. This longevity has implications for the possibility of life. On Earth, life appeared relatively quickly after the planet became habitable, perhaps within a few 100 million years of the Earth's formation. But complex multicellular life took much longer. Animals only appeared in the last 600 million years or so. Intelligent life, capable of building civilizations and pondering its place in the cosmos, appeared only in the last few 100,000 years. The process from simple chemistry to complex intelligence took billions of years. If a similar process were to occur on a planet around Proxima Centauri, there would be no shortage of time. A red dwarf provides a stable environment for trillions of years. Evolution could proceed at a leisurely pace. Complex life could arise, go extinct, and arise again many times over. Civilizations could rise and fall. Entire biological and cultural histories could play out on timescales that dwarf anything possible on a planet orbiting a sun-like star. Of course, this assumes that life can arise and thrive on such a planet in the first place. The radiation environment is harsh. The tidal locking may create extreme conditions. The lack of a day-night cycle could pose challenges for biological rhythms. Life as we know it evolved on a planet very different from Proxima b, whether life could adapt to conditions around a red dwarf is unknown. Some scientists are optimistic. Life on Earth has proven remarkably adaptable. It exists in extreme environments, in boiling hot springs, in acidic pools, in the crushing darkness of the deep ocean, in the dry valleys of Antarctica, inside rocks kilometers below the surface. Extremophiles, organisms that thrive in extreme conditions, demonstrate that life can tolerate a wide range of physical and chemical circumstances. Perhaps life around a red dwarf would simply be a different kind of extremophile, adapted to conditions we would find intolerable. Other scientists are more skeptical. They point out that life on Earth, despite its adaptability, still depends on certain basic requirements: liquid water, organic molecules, a source of energy, and enough stability for complex chemistry to develop. Proxima b may lack one or more of these. Without an atmosphere, it would have no liquid water on its surface. Without a magnetic field, it would be scoured by stellar radiation. Without a stable climate, any life that emerged might be repeatedly wiped out before it could evolve complexity. We simply do not know. The data we have are insufficient to answer the question, and the data we will be able to collect in the foreseeable future may also be insufficient. Some questions can only be answered by going there, by landing on a planet and examining its surface and atmosphere directly. For Proxima b, that prospect is so distant that it may as well be fantasy. But let us indulge the fantasy for a moment. Suppose, in some far future, humanity or its descendants develops the technology to send a mission to Proxima b. Suppose a spacecraft arrives there after a journey of decades or centuries. What might it find? The first thing it would notice is the star. Proxima Centauri would appear much larger in the sky than the Sun appears from Earth. This is because Proxima b orbits so close to its star, only about 7.5 million kilometers away. At that distance, Proxima would appear roughly 3 times the diameter of the Sun as seen from Earth. It would glow a dim red, casting a perpetual red twilight over the planet's surface. There would be no bright yellow sunlight. Everything would be tinted in shades of red and orange. If Proxima b is tidally locked, as expected, one side of the planet would always face the star. This dayside would receive constant illumination, though not constant warmth. Stellar flares would periodically flood the dayside with intense radiation, potentially sterilizing any exposed surface. The night side would face away from the star permanently, receiving only the faint glow of starlight from Alpha Centauri and the more distant stars. It would be extremely cold, possibly cold enough to freeze any atmosphere. Between the dayside and nightside, there would be a ring-shaped region of permanent twilight. This terminator zone, as it is called, might have the most moderate temperatures. It would receive some light from the nearby dayside, but not the full intensity of the star. It might be habitable in ways that the extreme dayside and nightside are not. If Proxima b has an atmosphere capable of circulating heat, this could moderate the temperature differences further, potentially making larger portions of the planet habitable. A spacecraft approaching Proxima b might first look for evidence of an atmosphere. Is there gas surrounding the planet? If so, what is it made of? Earth's atmosphere is about 78% nitrogen and 21% oxygen, with traces of other gases including carbon dioxide, water vapor, and methane. Mars has a thin atmosphere of mostly carbon dioxide. Venus has a thick atmosphere of carbon dioxide with clouds of sulfuric acid. Each planet's atmosphere tells a story about its history and current conditions. If Proxima b had an atmosphere with significant oxygen, that would be extremely interesting. Free oxygen is unstable. It reacts with other materials and gets bound up in rocks and water. On Earth, the atmosphere contains oxygen only because living organisms, particularly photosynthetic organisms like plants and cyanobacteria, constantly produce it. Without life, Earth's oxygen would slowly disappear as it combined with other elements. So finding oxygen on Proxima b would be suggestive, though not conclusive, evidence of life. But oxygen could also be produced by non-biological processes. Ultraviolet radiation can split water molecules into hydrogen and oxygen. The hydrogen, being lighter, might escape into space, leaving the oxygen behind. This process could, in theory, build up atmospheric oxygen without any life being present. Distinguishing between biological and non-biological oxygen production would require careful analysis of the atmosphere's composition and chemistry. A spacecraft might also look for water. Does Proxima b have oceans, lakes, or ice caps? Water is essential for life as we know it. It serves as a solvent in which complex chemistry can occur. It remains liquid over a range of temperatures that are compatible with organic molecules. Finding liquid water on Proxima b would suggest that the planet might be habitable, though it would not prove that life exists there. The spacecraft might take images of the surface, revealing landscapes unlike anything on Earth, or perhaps eerily similar. Geology depends on factors like the planet's size, composition, internal heat, and atmospheric pressure. Proxima b is probably rocky, based on its estimated mass. It might have mountains, valleys, plains, and craters like the terrestrial planets in our solar system. It might have volcanoes if it has internal heat. It might have ice formations if it is cold. The surface could be utterly barren, like the Moon, or complex and varied, like Earth. All of this is speculation. We have no data about Proxima b's surface. We have only indirect information about its mass and orbit. Everything else is inference and imagination. The planet could be radically different from anything we expect. It could have characteristics we have never even considered. The only way to find out for certain is to go there, which we cannot do. Let us step back from Proxima b and consider the broader context. The Alpha Centauri system is just one of hundreds of billions of star systems in the Milky Way galaxy. Most of those systems have planets. Some of those planets are in habitable zones. The numbers are staggering. Estimates vary, but a reasonable guess is that there could be billions of potentially habitable planets in the galaxy. Not all of them will actually be habitable. Many will lack the right conditions for life, but some fraction of them might support life, and some smaller fraction of those might support complex or intelligent life. These are guesses, not measurements. We do not have a reliable estimate of how common life is in the universe because we have only one data point: Earth. The Fermi paradox, named after the physicist Enrico Fermi, encapsulates this puzzle. If the galaxy contains many planets where life could arise, and if even a small fraction of those have produced intelligent civilizations, then some of those civilizations should be much older than ours. They should have had millions or billions of years to develop technology and spread across the galaxy, yet we see no evidence of them. No alien spacecraft, no artificial radio signals. No megastructures visible in astronomical surveys. The galaxy appears quiet and empty, as if we are alone. There are many proposed explanations for the Fermi paradox. Perhaps intelligent life is extremely rare, arising on only a tiny fraction of potentially habitable planets. Perhaps civilizations tend to destroy themselves before they can spread to the stars. Perhaps they exist, but choose not to communicate or expand in ways we would notice. Perhaps they exist, but the galaxy is simply too big and the distances too great for any civilization to span it in a detectable way. Perhaps we are the first intelligence to arise in the Milky Way. Perhaps we are simply not looking in the right way or in the right place. None of these explanations has been proven or disproven. The silence of the cosmos remains unexplained. Proxima Centauri, our nearest stellar neighbor, shows no signs of artificial activity. If there were technological civilization on Proxima b or in the Alpha Centauri system, we might expect to see evidence of it. Radio transmissions, waste heat, alterations to planetary or stellar properties. We see nothing of the sort. This does not prove that no such civilization exists. Absence of evidence is not evidence of absence, but it suggests that if life does exist there, it is not a spacefaring technological civilization broadcasting its presence. Search for extraterrestrial intelligence, or SETI, has been conducted for decades using radio telescopes and more recently, optical telescopes. The idea is that a technological civilization might use radio waves or lasers to communicate across interstellar distances. By scanning the sky for artificial signals, we might detect the presence of another intelligence. So far, despite many searches, no confirmed signal has been found. There have been tantalizing anomalies, like the famous WOW signal detected in 1977, but nothing that has been repeated or conclusively identified as artificial in origin. Proxima Centauri has been a target of SETI observations, given its proximity and the presence of an Earth-sized planet in the habitable zone. In 2019, astronomers detected a radio signal that appeared to come from the direction of Proxima Centauri. For a brief time, excitement built. Could this be the first evidence of an alien transmission? Further analysis revealed that the signal was almost certainly of terrestrial origin, probably interference from human technology. It was not a message from Proxima. The search continues. If we ever do detect a signal from another civilization, the implications would be profound. It would mean that intelligence can arise more than once in the universe. It would mean that the conditions for intelligence are not unique to Earth. It would raise questions about what such a civilization might be like, what they might know, and whether communication or even contact would be possible. It would change our understanding of our place in the cosmos. But that has not happened yet. For now, we are alone as far as we know. The only intelligence we are certain exists is our own. Earth is the only planet we are certain has life. The universe may be teeming with life or utterly barren, and we do not yet have the means to tell which is the case. Proxima Centauri will continue to burn for trillions of years. In that time, much can happen. Perhaps life will arise on one of its planets, if it has not already. Perhaps intelligence will emerge. Perhaps that intelligence will look up at the stars and wonder about the distant yellow star called Sol, wonder if anyone lives there, wonder if they could ever make the journey. Or perhaps not. Perhaps Proxima's planets are lifeless rocks, baked and irradiated and frozen, incapable of supporting anything resembling biology. Perhaps the flares are simply too intense, the conditions too harsh, the chemistry too unfavorable. Perhaps the planets will orbit their red dwarf host for trillions of years in absolute sterility, never producing so much as a microbe. We do not know, we may not know for centuries or millennia. The universe keeps its secrets well. The night sky, viewed from a location far from city lights, contains several thousand visible stars. Each of those stars is a sun, most of them with planets. Some are larger and brighter than our sun. Some are smaller and dimmer. Some are alone in space. Some are in binary or triple systems. Some are young, still surrounded by the disks of gas and dust from which planets form. Some are old, nearing the ends of their lives. Proxima Centauri is not visible in that sky, not to the naked eye. It is too faint, but it is there, in the southern constellation Centaurus, a dim red point of light that requires a telescope to see. It is the closest star, and beyond it, everything else stretches outward in a vast tapestry of light and distance. The Milky Way is a spiral galaxy, a vast rotating disk of stars with spiral arms and a central bulge. The Sun is located in one of the spiral arms, about 2/3 of the way out from the center. From our vantage point, we see the galaxy edge on as a glowing band of light stretching across the sky. That band is the combined light of billions of stars too distant to resolve individually. It has been called the Milky Way since ancient times because it resembles a river of milk spilled across the darkness. The nearest large galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. It is visible to the naked eye under dark skies as a faint fuzzy patch. The light you see from Andromeda left the galaxy 2.5 million years ago, when early human ancestors We're just beginning to use simple stone tools on the plains of Africa. Andromeda contains perhaps 1 trillion stars. It is slightly larger than the Milky Way, and it is approaching us. In about 4 to 5 billion years, Andromeda and the Milky Way will collide and merge, forming a single larger galaxy. This will happen around the same time that the Sun exhausts its hydrogen and begins its transformation into a red giant. When the galaxies merge, individual stars will probably not collide. Galaxies are mostly empty space. The distances between stars are so great that even when 2 galaxies pass through each other, stellar collisions are rare. But the gravitational interactions will reshape both galaxies, throwing stars onto new orbits, possibly ejecting some into intergalactic space. The night sky from Earth, or whatever remains of Earth, will look very different, if any observers are still around to see it. Proxima Centauri might be affected by the merger. Its orbit around Alpha Centauri might be disrupted. It might be thrown onto a new path through the merged galaxy, or it might survive intact, still bound to its companion stars, still orbiting the galactic center on some altered trajectory. Red dwarfs are survivors. They endure. The timescales involved are almost incomprehensible. Billions of years, trillions of years. Human civilization has existed for a few thousand years. Written history spans a few millennia. The entire history of our species is a few 100,000 years. We think in terms of days and years and lifetimes. The cosmos operates on scales that dwarf everything we know. And yet here we are thinking about it. We have evolved the capacity to contemplate the universe, to measure the distances to stars, to detect planets orbiting those stars, to wonder about life elsewhere. This is a remarkable thing. It may be the most remarkable thing about Earth. Among all the planets in the galaxy, at least one has produced beings capable of asking these questions. Whether any others have done so remains unknown. Proxima Centauri is a symbol of both connection and separation. It is connected to us by proximity. It is the nearest star. If we ever expand beyond the solar system, it may be our first destination. It represents the edge of our cosmic neighborhood, the beginning of interstellar space, the closest outpost of the wider galaxy. But it is also separated from us by a gulf so vast that we cannot cross it with current technology. That distance, 4.24 light-years, stands as a barrier between us and everything beyond the solar system. We can see Proxima, we can study it, we can even detect its planets, but we cannot touch it, we cannot visit, we cannot know it directly. This tension between knowing and reaching, between seeing and touching, defines much of our relationship with the universe. We are observers for now. We gather light, we make measurements, we build theories, we dream of journeys we cannot yet take. Perhaps someday the barrier will be crossed. Perhaps it will stand forever. Either way, the universe remains what it is, indifferent to our hopes and frustrations, governed by laws that do not care whether we find them convenient. Proxima Centauri will be there, regardless. A small, cool, dim red star, orbiting at the edge of a triple system, host to at least 2 and possibly 3 planets, one of them in the habitable zone, 4.24 light-years from Earth, unreachable but not unknowable. It is the closest star we will never reach. And it is beautiful in its own way, as all stars are beautiful, points of light in the darkness, furnaces of fusion, beacons of a universe far larger than anything we can comprehend. There is no grand conclusion to be drawn, no lesson that ties everything together neatly. The universe does not provide lessons, it simply exists. We observe it, describe it, and try to understand it. Proxima Centauri is part of that existence. So are we. For a brief moment in cosmic time, we overlap. We share the same galaxy, the same neighborhood, the same laws of physics. What we make of that overlap is up to us. The light continues to stream across the void. It left Proxima about 4 years ago and is arriving now, a tiny portion of it captured by our telescopes, analyzed, recorded. More will follow. The stream never ends. It carries information about a star that has been burning since before the Earth existed and will continue burning until long after everything we know has changed beyond recognition. That is Proxima Centauri, the nearest star, the closest sun beyond our own, so close and yet so far, always there in the southern sky, waiting for us to learn how to reach it, or simply waiting, as stars do, with the patience of entities that measure time in billions and trillions of years. There is nothing more to say about it for now. The facts are what they are. The distances are what they are. The possibilities remain open, the questions unanswered, the future unwritten. Proxima burns on, as it has for nearly 5 billion years, as it will for trillions more. A red dwarf star, one among hundreds of billions, distinguished only by its proximity to one small world where beings evolved who could notice it and wonder what it meant. That wondering is perhaps the most human thing of all, to look at a point of light impossibly far away and ask, what is it? How did it form? Is anyone else there? Can we ever go? These questions may or may not have satisfying answers, but the asking itself is meaningful. It connects us to something larger than ourselves, larger than our planet, larger than anything we can directly experience. Proxima Centauri does not care whether we ask these questions. It is a ball of hydrogen and helium undergoing nuclear fusion, not a conscious entity. It has no preferences, no awareness, no concern for us. But we care. And that caring, that curiosity, that drive to understand is what has brought us this far. It is what might someday bring us farther. For now, we remain here, on Earth, looking up at the sky, measuring the light from distant stars, imagining what might be possible. Proxima Centauri is the first step on a staircase we have not yet learned to climb. The staircase stretches outward in every direction, to stars and galaxies beyond counting, to reaches of the cosmos we can barely imagine. The first step is the hardest. It is also the closest. 40 trillion kilometers, 4¼ light years, the nearest star. The closest star we will never reach.